Hi friends, let us continue discussion on Turing machine. Let us discuss gate questions on decidability. The question is, which of the following is or undecidable? Option A, given two Turing machines M1 and M2, decide if L of M1 is equal to L of M2. That is language of M1 equal to language of M2. Given a Turing machine M, decide if language of M is regular. Next option, given a Turing machine M, decide if M accepts all strings. Last option, given a Turing machine M, decide if M takes more than 1073 steps on every string. Option A, there is no general algorithm or Turing machine that can take any two machine description and correctly determine their equivalence in a finite amount of time. That is, to check whether two Turing machines accept the same language is a undecidable problem. Option B. There are Turing machines which accept regular languages and Turing machines which accept languages that are not regular. But whether a language is regular or not, it is a semantic property that is having to do with what is in the language, not with the form of the Turing machine. So, by Rice theorem, it cannot be decided whether L of M is regular. Option C. To check if M accepts all strings, a decider would need to simulate an infinite number of strings and ensure that for every string halts and accepts. So both B and C are undecidable. Option D. A Turing machine sees at most the first 1073 symbols of input in its first 1073 steps. Hence, whether it stops on first 1073 steps depends only on the first 1073 symbols of input. So, the string length is finite. It gives a way to decide this. So, it is decidable. So, what is the final answer is the options A, B, C are undecidable. D is decidable. So answer is A, B, C. Next question, which one of the following is not decidable? So let us see option A. Given a Turing machine M, a string S and an integer K, M accepts S within K steps. So we can find out whether the Turing machine M accepts the string within a finite number of steps. So it is decidable. What about option B? Equivalence of two given Turing machine is not decidable. C. Option C. Language accepted by a given finite state machine is not empty. So we can easily verify by generating at least a single string through this finite state machine. So it is decidable. Like that, language generated by a context-free grammar is non-empty. So again, we can generate at least a single string. So to prove that it is a non-empty. So the answer is option B, that is undecidable. So the answer is option B. Let us further explain the concepts. The problem of determining whether a given Turing machine accepts a string within finite number of steps is decidable. The language accepted by a finite state machine is non-empty if there exists a valid path from the start state to any final accepting state. So again, this is also decidable. A context-free grammar generates a non-empty language if the start symbol can derive a string containing only terminal symbols. So this is also decidable. Let us understand the difference between deciding and recognizing. A machine M1 decides a language L if it halts on every possible input. Specifically, it must enter an accept state for all strings W it belongs to L and a reject state for all W it doesn't belong to L. But what is recognizing? A machine recognizes a language if it enters an accept state for every string W belongs to L. However, for W doesn't belong to L, it may either enter a reject state or loop forever. Turing machines are equivalent if they accept the same language, that is, recognize the same set of strings. Constructing equivalent machine is simple, but determining whether two arbitrary Turing machines are equivalent is undecidable.